Hello, so you are welcome. Today our discussion is on capacitance and dielectrics and how dielectrics affect the capacitance of a capacitor, like types of capacitors, the arrangements of capacitors that we have. That's our discussion today. Now, a capacitor, taking into consideration a parallel plate capacitor, has two metal plates, each of area A, and the plates have equal and opposite charges, meaning the charges on the plates are the same but they are opposite. Now the magnitude of the electric field between the plate is given by E equals K over epsilon naught A. Now the equation can be simplified into charge density over epsilon naught, where charge density is equal to K over A. So charge density K over A is the charge per unit area. So the electric field can be simplified into charge density over epsilon naught. Now, electric field of a capacitor does not depend on the distance from the charges. So looking at the charges on the plate, the distance separating the charges do not affect the electric field of the capacitor. But therefore, taking into consideration the quantity of the charge and the area of the charge, these are the parameters that affect the electric field of the capacitor. Now, a capacitor is a device that stores charges. So capacitors store charges. And examples of application of capacitors are radio receivers, RAM chips, filters, in power supply, and many more. Now, capacitance of a capacitor is the ratio of the magnitude of the charge on either plate to the potential difference between the plates. So the magnitude of the charge on both plates and the potential difference between the plates having their ratio gives the capacitance of the capacitor. That is, K is proportional to V, meaning as the charges increasing, the potential difference will be also increasing. Now, mathematically, we can say that capacitance equals K over change in V, over change in V. Now, the SI unit of the capacitance is coulomb per volt, or farad. So, the capacitance of a capacitor is calculated in farad or coulomb per volt. Now, capacitance is always positive. It's always a positive quantity. That is, the sign of the charge does not affect the capacitance. We don't take into consideration either it's positively charged or negatively charged, but the magnitude of the charge, that is what we take into consideration for capacitance. And the capacitance of a given capacitor is always constant. The capacitance of a given capacitor is always constant. Now, parallel plate capacitor. Each plate is connected to a terminal of the battery, which establishes an electric field in the connecting wires when the capacitor is uncharged. So when we connect the terminals of the battery to the plate, an electric field is generated in the connecting wires. Now, the field that's generated apply a force on the plate. So it applies a force on electrons on the plate, causing them to move onto another plate. So the force moves the electrons from one plate onto the another plate. And when the electrons are moved from one plate to another plate, the one losing electrons becomes positively charged, and the one gaining the electrons becomes negatively charged, therefore giving out the opposite charges of the plate. So we should take into consideration, or so we should take note of that. When the electrons are moved from one plate to another, one becomes negative and one becomes positive, and their magnitude are the same. Their magnitude are the same. So looking at the diagram we have here, we're having two plates, same quantity, opposite signs. Then the area of the plate are the same. Then the separation between the plate. Now, as we said earlier on, charge density on the plate is the charge over the area of the plate. So the capacitance is proportional to the area of the plate and inversely proportional to the distance between the plates. So as you can see in the equation here, C is proportional to the area of the plate and inversely proportional to the distance between the plate. So your larger your area, the larger the capacitance, the smaller the distance between the plates, the larger the capacitance as well. So we should take note of this relation. Now we've already seen earlier how charges and potential difference affect the capacitance. Now we are looking at the area and the distance between the plates, how they affect the capacitance. Now the electric field is given by Q over epsilon naught A, where Q is the charge, epsilon naught is the permittivity of free space, then A is the area. Then we can simplify it into charge density over epsilon naught, as we have seen that earlier on. Now capacitors in parallel. Now we are coming to look at when two or more capacitors are connected in a circuit, the mode at which they are connected and how their capacitance can be determined. The electrons in the plate are transferred from the left plate through the battery to the right plate, making the left positive and the right negative. So when we connect two capacitors parallel, when you connect them parallel, the electrons from the left plate are moved to the battery, then they come into the right plate. They move from the left through to the battery, then they come into the right place. That's the flow of electrons when the capacitors are connected parallel. Now the flow of charges ceases when the voltage across the capacitor equals that of the battery, leaving the capacitor at their maximum charge. So when the charges flowing ceases up, meaning the voltage across the capacitor is equal to the voltage of the battery, meaning the capacitor has reached its maximum charge. So the total charge equals the sum of the charges on the capacitor. So we sum up the charges on each plate of the capacitor, or sum up the charges of the capacitor. So capacitor 1 will have Q1, capacitor 2 will have Q2. The potential difference across the capacitors is the same. So V1 is equal to V2, which is equal to V. So the potential difference across them is the same. Now the total capacitance, which is termed as equivalent capacitor, is therefore given as C of EQ equals C1 plus C2. So for parallel plate, it is just straight summation. We sum up the capacitance of each plate, and we know that capacitance equals Q over V. So therefore we're having Q1 over changing V plus Q2 over changing V. So this gives the summation or the equivalent capacitor. Now looking at the diagram here, the capacitors are connected parallel. So the charges or the electrons move from the left plate here. So this left plate, they move then to the terminals of the battery. They enter the battery, come out, then to the right plate of the capacitors. But the current move in the opposite direction of the flow of the electron. So we should know that. Now in capacitors in series, the electrons are transferred from the left plate of C1 through to the right plate of C2, then through to the battery. So the right plate gain the negative charges, then the left plate having positive charge since the electrons are leaving that plate. Now the charges on each plate are equal. They have the same amount of charge flowing through both capacitors. Then the potential difference across the capacitors, they add up to the battery voltage. That is, we sum up the potential difference across capacitor 1, then that of capacitor 2 to get the total voltage. And this voltage must be equal to the voltage that the battery is giving out. Now the equivalent capacitor or the total capacitance will be equal to 1 over C equals 1 over C1 plus 1 over C2. So with this one, we find the inverse of their capacitance, then we sum them up. We find the inverse of the capacitance, then we sum them up. So using the equation of capacitance, we are having change in V1 over K plus change in V2 over K since it is inversed. So this is how we find the capacitance in series. Now, energy stored in a capacitor. The work done to transfer a charge from one plate to the other is given by K squared over 2C. So the equation for work done, or the energy stored in the capacitor, since energy is the same as work done, we have W equals K squared over 2C. That is the energy stored in a capacitor. Now, we know that K is equal to CV. K equals CV. So we can do our substitutions having W equals CV squared over 2. CV squared over 2. So we take note of that. Now, dielectric constant. A dielectric is a non-conducting material that increases the capacitance of a capacitor when placed between the plates. So when we insert a dielectric material between the plates of a capacitor, the capacitance of the capacitor is tend to increase. It is tend to increase. And these materials are not conducting, meaning they are insulators. So examples are rubbers, waxed papers, we have plastics, and even consider air as one of the dielectric materials. So dielectric increases the capacitance by changing or reducing the electric field between the plates. The electric field between the plates is reduced, which therefore increases the capacitance of the capacitor, and this is done by the dielectric material which is inserted between the plates of the capacitor. The reduction in the electric field is described by the electric constant. Is described by the dielectric constant K, which is the magnitude of the field without dielectric to the magnitude of the field with dielectric. So having K to be equal to E naught over E, where E naught is the magnitude of the field without a dielectric and the magnitude of the field with the presence of a dielectric. Now, the geometry of the plate and the dielectric constant of the material between the plates affect the capacitance. So the geometry is the area and the separation distance of the plate. Then the dielectric constant K also affects the capacitance of the plate. So we are having C to be equal to K epsilon naught A over D. K epsilon naught A over D. Now for K to be equal to 1, that is when there is no dielectric present. We go back to our normal equation, which is C equals epsilon naught A over D. So when we have air between the plates, meaning there's no dielectric present, which gives K to be equal to 1. Now let's look at some examples. A parallel plate capacitor has a plate area of 0.05 meters squared and a plate separation of 4 millimeters. If the capacitor has no dielectric that is occupied by air, calculate the capacitance of the capacitor. Then take epsilon naught to be equal to 8.85 times 10 to the power minus 15 farad per meter. So now let's look at our solution. So firstly, we state out our equation. C equals K epsilon naught A over D. So after stating out the equation, we write out our parameters given in the question. We have A to be 0.05 meters squared, D equals 4 millimeters, K equals 1, then epsilon naught, which is equal to 8.85 times 10 to the power minus 15. Now let's do our substitutions. So we substitute our K, which is 1, then epsilon naught 8.85 times 10 to the power minus 15, then our A, which is 0.05, then the D, change it to meters, which gives us 4 times 10 to the power minus 3. So after computing, we're having our capacitance for the capacitor to be equal to 1.11 times 10 to the power minus 13 farad. 1.11 times 10 to the power minus 13 farad. So this is the capacitance for this parallel plate capacitor. Now let's look at another example. A 12 times 10 to the power minus 6 farad capacitor is charged to a voltage of 200 volts. Calculate the energy stored in the capacitor. So to our solution, The equation that will be used for this problem is W equals CV squared over 2. CV squared over 2. So stating out our parameters in the question, C equals 12 times 10 to the power minus 6 farad. Then V is 200 volts. So we do our substitutions. That is, we insert our C, we insert our V, then we compute it to get the work done or the energy stored in the capacitor to be 0.24 joules. So the energy in the capacitor is 0.24 joules. Now another question. 3 capacitors, C1 which equals 5.4 microcoulomb, C2 which equals 3.6 microcoulomb, and C3 which equals 11.7 microcoulomb are connected in a circuit. C1 and C2 are connected in parallel, and the combination is in series with C3. Find the total capacitance. So if we marginalize the diagram, we have C1 and C2 being connected parallel. They are connected parallel. Then their combination is therefore connected in series to C3. So picture the diagram as such. So now let's look at our solution. So the capacitors that are connected in parallel, the equation that will be used to calculate their total capacitance is Cp equals C1 plus C2. So we use Cp to denote capacitors in parallel. Now we know C1, we know C2, so we do our substitutions and compute it to get Cp, and this value gives us 9 times 10 to the power minus 6 farad. So after that, we compute for capacitors in parallel, and this will give us the total capacitance because we've done that for parallel. So calculating the combination and C3 will give us the total capacitance in the circuit. So capacitors in series is giving us 1 over C equals 1 over Cp, which is the total, plus 1 over C3. So now we do our substitutions. Cp, as we calculated earlier, is 9 times 10 to the power minus 6. Then C3 is 11.7 times 10 to the power minus 6. So after computing, we are having C to be equal to 5.09 times 10 to the power minus 6 farad. 5.09 times 10 to the power minus 6 farad. So this is the total capacitance in the circuit. So here are some trial questions that you can try your hands on. Then you give your final answer in the comment section.